Okay, so this is percentage appreciation, depreciation, just some more practice using this skill of calculating a repeated percentage change with a mixture of increase and decrease. So the first example we're going to look at is this one. So unfortunately, unlike the vintage cars that we've seen before, most cars do not appreciate in value, they actually go down in value, as I'm sure you're aware. So in this example, we've got a car is bought for £12,000 and it depreciates by an average rate of 13% every year. Now, in reality, it's kind of a flattening out curve that depreciates a lot, and early on in the first year, then it depreciates again, but not quite as much, then not quite as much, and not quite as much the following year. So it wouldn't be, a straight kind of line of it going down, but we're saying that it depreciates by an average rate of 13% every year. And we're asked what would be the value in 4 years' time, rounded to three significant figures. So we are going to, first of all, have to work out what is our multiplier for a decrease by 13%. So some of you may be able to go straight to the decimal, but if you are making mistakes with that, then just write it out in full. 100%, we are taking away 13%, so that means we have 87% left. Changing that to a decimal by dividing by 100 makes it 0.87. Okay, so the after 4 years, the value is going to be 12,000 multiplied by 0.87, and that would be decreasing it once by 13%, but I want to do it 4 consecutive times, so to the power of 4. So now just put that into your calculator, and you'll see that gives you a value of 6874.77, etc, etc. I've been asked to round to 3 significant figures, so let's do that now. So that's going to be, the third significant figure is going to be that 7. Remember, anything after that up to the decimal point is going to turn into a 0. So that's going to be 6, 8, that's going to stay as a 7, and that's going to turn into a 0. So 6,870 to 3 significant figures. Let's look at another example. So we've got, this time, the bacteria growth rate in a laboratory sample increases by 50% every hour. If the initial bacteria population in a sample is 30,000, what will the population be after 2 hours? What would it be after 5 hours? And then during which hour will the bacteria population exceed 10 million? Okay, so we've got a few different calculations to do. So the multiplier that we need to work out, first of all, that's increasing by 50%, right? So 100% plus 50% is 150%, divide that by 100, so our multiplier is going to be 1.5. So after 2 hours, what would the population be? So it's going to be 30,000 times 1.5. Now, it's not years this time, it increases every hour. So that's why after 2 hours, we can still do to the power of 2. Okay, so the kind of unit time is not every year, which it is in the previous question. This is the percentage changes every hour. So it's, what do we want to do after 2 hours? So it's to the power of 2. 30,000 times 1.5 to the power of 2. And the population is 67,500. Okay, what would the population be after 5 hours? Well, we're going to do 30,000 times 1.5 to the power of 5. So 30,000 times 1.5 to the power of 5. That gives me an answer of 227,812.5. And then question C, during which hour will the population exceed 10 million? Well, we already know that after 5 hours, the population is 227,812.5. So then what would it be after 6 hours? So what we do with that answer is we're actually just going to do a bit of trial and error, and we're just going to times that answer by 1.5. And then we're just going to keep doing that until we get to our population to be above 10 million. So after 6 hours, just hit that answer times 1.5. So 341,718.75. Okay, so we're not there yet. After 7 hours, again, just do times 1.5. And if you've got the answer times 1.5 in your calculator, you can just actually hit the equals button and it times it by 1.5 again. So that takes me up to 512,578.125. What about after 8 hours? That's gone up to 768,867.1875. After 9 hours. Okay, after 9 hours, my population is 1 million. Sorry, that's yes, that's meant to be when is it going to exceed 1 million? Sorry, not 10 million. So 1,153,300.781. So after 9 hours, it was over the 1 million limit. That was meant to be 1 million, not 10 million. So during which hour? So it is during the 9th hour is when it would exceed that. Okay, one more example. And it is based on the world population. So the world population is increasing by approximately 1.1% every year. If the growth rate remains at this value, calculate the world population in 20 years' time. So round to 3 significant figures. Right, okay, so the time period is 20 years. The multiplier is 100 plus 101, that's 101.1, so that's going to be 1.011. And the population now, what's population right now? Don't know, but what I've got here is a link which you won't be able to see pop up, but it's popping up on my screen and it takes me straight to the current world population. And my screen is telling me that it is 7,851,195,000. So let me write that down. So it's 7,851,000,000. We're almost actually at 8 billion people now, which is a bit scary. 195,000, and then it's constantly changing. So 972, let's call it. So that is approximately the number of people that are on the earth right now. 7,851,195,972 people. So what is the population in 20 years' time? Well, we have to take this starting value. We have to multiply it by our multiplier, 1.011. Okay, that's an increase of 1.1% to the power of 20. So carefully put that calculation in. And it goes up to 9,771,448,100. So in 20 years' time, if the growth rate remains approximately the same, we'll be almost 10 billion people. And there's a kind of wider question, you know, a wider discussion to have around that. And is this a problem? The population is currently 7.8 billion. 20 years' time, if we keep going the same rate, it's going to be 9.7 billion. Is that going to cause an issue? And if so, why? What do you think are the issues with that? Okay, for in class, we could discuss this, but I just want you to have a wee think about what do you think are going to be the issues surrounding that percentage increase.